I think everyone is here. So the next speaker is Dipranjan with GFF level set percolation on finite graphs.
Thank you. First of all, I thank the organizers, Trishen, Piet, and Subhajit for inviting me. And it's always feel nice to be here in ICTS. So I will be talking about GFF level set percolation on finite graphs. So this is joint work with my supervisor, Subhajit Goswami. Okay. So besides infinite graphs, percolation on finite graphs has a long and rich history. So classical model includes Erdős-Renyi random regular graphs, etc. And more recently, random graphs with general degree distribution have attracted significant attention. So for example, configuration models, preferential attachment models, random graphs with power law degree distribution, etc. So Bernoulli percolation on various deterministic graphs has been studied extensively. For example, Alon, Benjamin, and Stacy, they studied for a sequence of finite deregular expander graphs, and they identified the critical probability to be 1 by d minus 1, which is same as the critical probability of infinite deregular tree. Nachmias also did the Bernoulli percolation on expander graphs with unbounded degree, and he derived mean field condition, mean field behavior on these graphs. Also, Borgs and Slade et al., they studied Bernoulli percolation on various products of finite graphs, and also Hofstad and Nachmias. And Itai Benjamini had a conjecture that for any vertex transitive graphs, the like in the supercritical phase, there will be unique giant component. So Philippe Esso and Tom Hutchcroft, they proved in this paper that this conjecture is indeed true in full generality. Okay. So one of the main questions in finite graphs is that under what conditions on a finite graph we can expect mean field behavior. So what is mean field behavior? I will briefly mention. So for Erdős-Renyi, so you open each edge with probability P and close each edge with probability 1 minus P. So if you take P equal to C by N, then if C bigger than 1, you have supercritical phase, that is unique giant component arises here, and the size of the largest cluster is some C type N. And for C less than N, it is subcritical phase, and your volume of the largest cluster is order of log N, right? And what happens in the criticality? If you take P equal to 1 plus epsilon N by N, and if n to the power 1/3 times epsilon n tends to infinity, then size of the largest cluster by n to the power 2/3, this tends to infinity with high probability. And if n to the power 1/3 times epsilon n, this tends to minus infinity, then largest cluster by n to the power 2/3 tends to 0. So this is actually mean field behavior. Now, so Borgs and Slade et al., they have a series of papers, and they defined a finite version of triangle condition, which is originally introduced by Eisman and Newman for infinite graphs, and they derived this condition for finite transitive graphs. So what is the triangle condition? So this is delta p x y is summation u v in p. This 2-point function. So you connect to xu, and then you connect to u v, and then you connect to vy, where tau p is probability that x tau p of, let's say, xy. So x and y is connected by an infinite open path. So they came up with this condition. For finite graphs, they define the critical probability to be the unique solution of this quantity, where chi p is the susceptibility, the size of the expected size of the cluster. And they came up with for p less than equals to pc. So the pxy is less than equals to indicator x equal to y plus some constant times degree, d is the largest degree, plus some constant time susceptibility to the power q by mod v. So this is a finite version of triangle condition, and they can show that if this satisfies, then you observe mean field behavior. That is, volume of the largest cluster is theta mod v to the power 2/3 in a window of 1 by d times mod v to the power minus 1/3. And sorry, it is connection. So x and y is connected. PC is the critical probability. So for finite graphs, they have defined the critical probability to be the unique solution of this equation. And for P less than equals to PC, if condition holds, then you observe that. And they verified in the second paper, they verified this triangle condition for various product life graphs like high dimensional tori, etc. So this triangle condition and using, they verified this condition using less expansion, what Professor Slade already introduced to us in his mini course. So often this condition is not always easy to verify. So Nachmias came up with a different condition for finite transitive expander graphs with large girth, and his condition is based on a non-backtracking random walk, transition probabilities of non-backtracking random walk on the graphs, and he can show that this condition is satisfied by expanders with large girth of order of log n. And if this satisfies, then he can derive that the largest cluster is again theta of mod b to the power 2/3, and the size of the critical window is 1 by d to the power 1 by d times mod b to the power 1/3. Okay, so our motivation was to, so can we come up with a model with minimal assumptions that exhibit mean field behavior? So maybe outside of Bernoulli percolation. So there are possible candidates, for example, correlated percolation models such as level set percolation of the Gaussian free field and other Gaussian free field, also random interlacements and its backend set. So these are studied for infinite graphs. So if we want to study them on finite graphs, we have to make analogous definition there, because finite graph is recurrent and you cannot have the usual GFF. So there are other ways to do it. For example, you can add a killing rate to each vertex, or you can define a killing region in the graph. But this depends on the geometry of the graph, and you have to understand the behavior of the random graph, behavior of the random walk on the graph. So it turns out that the zero average GFF is a canonical version that you can define on the finite graphs. So Abertzelli, in the first paper, he introduced zero average GFF for this discrete torus, and then Abertzelli and Sarny, they studied zero average GFF for zero GFF on deregular expander graphs, and Sarny also studied zero average GFF on expander graphs, and he proved that unique giant component arises in the supercritical regime, where the largest and the second largest cluster has volume some delta times mod v, and not order of log mod v. And Guillaume Conchon Karjan, he studied zero average GFF for random regular graphs with respect to annual probability measure. So it turns out in our analysis that the level set percolation of zero average GFF on metric graphs is a suitable model where we can observe mean field behavior. So now comes part one. I'll describe the model and main result. So assume that G is a finite simple connected graph. We are not assuming it is transitive, and it can be regular, and we are not assuming it assuming large curve. It can have small cycles. So spectral gap is bounded below by some constant lambda, and maximum degree is D. So for the time being, assume that D is bounded, but we have also results when D is not bounded. So now consider the Dirichlet form defined by this quantity, where f is a function on the graph G, and spectral gap can be expressed via Dirichlet form in this type of variational formula. Okay, so the spectral gap is very important for us, that I will show you in the later. Okay, so now you will consider metric graph of associated to the graph G. So Professor Rodriguez already introduced these terminologies to us in his mini course. So metric graph is also known as cable system, is obtained from G by replacing each edge with a unit open interval, and the intervals are glued together to a particular vertex if there are many intervals coming out of that edge. So zero average GFF is a centered Gaussian field with covariance given by the zero average Green's function. So zero average Green function. So consider xk is a lazy random walk on Z. Then zero average Green function is defined as, so 1 by dy. Dy is a degree of the vertex y. Sum k bigger than equals to 0. Probability. So starting from x, you will visit y minus the stationary measure. So this is the zero average Green function, and it satisfies this zero average condition. Summation dx times phi x is equal to 0. Now this zero average, so this GFF is defined on G. We have to define it on the metric graph G tilde. So for two vertex, so for example, this is phi x and this is phi y. So vertex x and vertex y. So interpolate. So conditioned on phi x and phi y, we interpolate the zero average GFF on the interval by a Brownian bridge. Brownian bridge of length 1 with marginal values phi x and phi y. And this is introduced by Lupu in this famous paper. So our primary objects of interest are these level sets, where a set of all x in G tilde such that phi x is bigger than equals to h. So h belongs to R is any parameter. Okay. So now this level set percolation on G tilde induces a bond percolation on G. So we call an edge open if the whole interval belongs to the G tilde bigger than equals to H. And condition on vertex values phi x and phi y. So the edge will be open with this probability. So this also, so Professor Rodriguez also mentioned this probability, that is, so you have to have this Brownian bridge above value h. So this is, let's say, phi x, and this is phi y, and in the whole interval, the Brownian bridge is bigger than equals to h, and that probability is given by this. And this induces a kind of inhomogeneous bond percolation on the graph G. Okay. So let G bigger than equals to H be the resulting random subgraph with this bond percolation, and let Cx bigger than equals to H denote the cluster of any vertex X, and Cmax denotes the largest cluster. Okay. Now I can come to the main result. So the critical window is mod v to the power theta mod v to the power minus 1/3. And if you take h is equal to a mod v to the power 1/3, where a belongs to the real numbers, and for any delta, you can observe this type of bound, where this constant depends on the degree and the lower bound on the spectral gap. So we can observe that the size of the largest cluster is order of mod v to the power 2/3, and that we can observe in Erdős-Rényi random regular graphs. So this is the mean field critical behavior we observe in the graph. So this result is for critical window. So let's see what happens outside the critical window. So if you take h is equal to mod.
Back to the here, yeah, just for 30 seconds.
So outside critical window, so if you take h equal to mod p to a times mod b to the power minus 1/3, that is, and let a positive. So this is kind of supercritical phase. The supercritical phase, we subcritical phase, we observe that largest cluster has volume log mod v, some constant time log mod v, and again this constant can be dependent on d and lambda. And whereas in the supercritical phase, where you take h is equal to minus a times mod b to the power 1/3, then we can observe that the largest cluster has volume some c times mod v. So giant component arises in the supercritical phase. And from these two results, we can conclude that h equal to 0 is the critical threshold for the phase transition in this percolation model. So this is the exact mean field behavior what we observe in case of Erdős-Rényi and graphs. Okay. So to prove this kind of results, we need some kind of control on the geometry of the graph. So here we are not assuming any large girth condition. So several approaches on the percolation of expander graphs relies on the graph being locally tree-like, and that is guaranteed by the large girth condition. So we are not assuming large girth here. So, And also there can be, so graphs, example of graphs, there can be globally expanding, but not locally tree-like. So we need a tool that depends only on mod B, D, and the spectral gap, and that gives us the control of the geometry of the graph. And this is precisely where the zero average capacity enters in the picture. Okay, so what is zero average capacity? So to define that, so we have to define the Dirichlet form on the metric graph. So if you take a f function f on G, we extend the function on the metric graph by interpolating linearly on the intervals, so that on the intervals the function is continuous and differentiable. So the Dirichlet form of the metric graph is defined by this integral, where rho is the length measure of the metric graph G tilde. So then we consider this variational problem. So let K be a compact subset of G tilde with finitely many components, but K does not contain the whole of B. Otherwise, this variational problem does not make sense. So this function f restricted to K is equal to 1, and it satisfies this zero average condition, summation dx time fx equal to 0, and this f minimizes the Dirichlet energy E tilde f comma f. So let us call the minimizer fk. So fk, so this fk is actually a harmonic extension of the function 1 to the whole of G tilde. So yeah, so with respect to this zero average condition. Okay, then zero average capacity of K is defined by this quantity. So Dirichlet energy of this Fk comma Fk, and which is equal to the 2 mod D times nu K. And we are calling this zero average capacity because for transient graphs, the capacity can be also characterized as a variational problem using Dirichlet form. So, but here we have this zero average condition, so we are calling it to be zero average capacity of K. And for graphs with positive spectral gap, it behaves like linear isoperimetric functional on K intersection P. So for so there exists constant depends on D and lambda, such that the zero average capacity is lower bounded by C times K intersection B, and so this comes from the spectral gap, and if K is connected with K intersection B plus 1 is less than equals to some C times mod P, then you have the upper bound, which is also depends on mod K intersection, cardinality of K intersection B. So if you consider the zero average capacity of a singleton set, so this is actually finite, right? But if you then add them up and consider the zero average capacity of the whole set V, then this is infinite, right? So the zero average capacity does not depend on the volume of the K, but it should depend on the cardinality of K intersection. And this, sorry. And this result actually is a crucial bridge from the geometry of the graph to obtain the cluster volume bounds. So this result helps us to derive various. So we will derive some lower bound. So on the some tail bounds on the cluster volume, and this is a crucial lemma that will allow us to do. Okay. With this, I came to the part 2 of my talk, exploration, martingale, and Brownian comparison. Okay, so this is a brief strategy of the proof. So first we explored the level set clusters in G tilde via a random growing sets KT, and so we will define an exploration that will give us the family of random sets KT, and then attach a martingale MT with MT will from the Dirichlet pairing of phi with FK. Then we show that the quadratic variation of this martingale is actually the zero average capacity of the set KT. Then we apply Dubin-Schwarz theorem to conclude that if you time change the martingale by its quadratic variation, then it is actually a Brownian motion. Brownian motion, and whose times parameter will be the zero average capacity of the set. And then we convert the event existence of large cluster into the Brownian motion has a long excursion above a moving boundary. So we convert the event of there exists a large cluster to some Brownian probabilities that we can easily calculate, and from that we obtain various tail bounds for the largest cluster. And this whole strategy is inspired by Ding and Wirth. They studied the level set percolation of Gaussian free field on metric graph of DT. So FKT is the minimizer that we got from the Dirichlet energy by minimizing this EFF. So we with zero average condition, dx fx equal to 0 and f restricted to k is 1. So fk is the minimizer, then you put kt. Okay. So now comes the exploration process. So we will build a family of random compact subsets of G tilde using a certain breadth first search in the metric graph. So how we will do that? With some desirable properties. So choose a vertex V and consider a ball of radius 1 by n. So take n bigger than 1, and so this is the ball, and let's say you have these intervals. So I will start from the initial set boundary of this ball, and I will look at the points intersected with the G tilde bigger than equals to each. And let's say this is this point. So let's say this is x1 prime, this is x2 prime, and this is x3 prime. And let's say these are the vertex. So this is V, the neighbors of V's are here x1, this is x2, and this is x3. Right. Then I will look at the xi double prime is supremum of x belongs to this interval, xi prime comma xi, such that xi prime comma x, this belongs to the level set G tilde. Right. Then I will define certain points, so certain random stopping points. So let's say tau 1, which will be defined by this summation rho xi prime comma this x double prime, that psi runs from 1 to 3. So we will do the explorations such that it is continuous on the metric graph. Then define kt. So okay, so let's say dt with the unique index such that rho this xi prime comma xi double prime less than t less than equals to t less than summation dt such that rho xi comma xi double prime. Then define kt as k naught union I runs from 1 to dt dt minus 1 xi and union x prime x double prime dt triple prime dt and x triple prime dt such that the volume of x rho x dt prime comma is t minus the volume of this quantity. So these explored sets are such that their volume is t and they are increasing as time increases. And they satisfy some measurability condition such that if you take any open set U.
I understand the KTs. So what you have K0 union. Why rho is the measure, right?
Rho is the length measure of this interval.
Yeah. Yeah.
Oh, sorry, not here.
So okay, then you.
So these intervals.
Right. Okay. So that's here. And then what did you say about the prime to prime prime?
So this so let's say this is x1 prime, then I am looking at x double prime, which is the x double prime is such that these intervals belongs to the set G tilde bigger than equals to. And we are all defining in each interval, we are defining this x double prime. This is x3 double prime. And then we are summing up all these lengths. That will be my first random time point up to which I will look. Right? Then you define KT such that the volume of KT is T with suppose the T is such that your T is such that your length is this part, right? So then you take K naught union this interval. This is KT.
Okay, thanks.
So these KTs are increasing and they satisfy certain measurability condition. So for any open set U, subset of G tilde, the KT subset of U, this event belongs to the sigma algebra generated by U, where Fu is phi x such that x belongs to U. And so since this zero average GFF has this zero average condition, we don't have usual Markov property as GFF, but we can characterize the conditional distribution of phi restricted to K. Okay. Then we got this, then we define an exploration martingale. So for a nice compact set K, which is a compact set with finitely many connected components, and so it is not whole of V. So V minus K is not equal to phi. Then we define this martingale, which is Dirichlet pairing between phi and this Fk, where Fk was that minimizer. And this Mk is actually a martingale. So this given by this relation with respect to the filtration generated by the field inside the set K. And furthermore, we have this decomposition of the martingale. So this martingale can be written as two parts, where the first part is based on the values of K intersection V. So we are calling it the bulk term. And the second part, we are calling it boundary term because it depends on the boundary of K. And these two terms will be very important for us for deriving various tail bounds. Then you define a martingale M tilde T, which is Mk. And M tilde T is a continuous martingale with respect to the filtration generated by the sets K. So this is exploration martingale. And now we will show that this martingale has quadratic variation. Okay, no, we have again the properties of exploration martingale. So if you take K is subset of G tilde bigger than equals to H, then Mk is bigger than equals to H times the zero average capacity of the set K. So for large clusters, so this martingale will take large values, right? But the reverse direction is not obvious. So we have two terms, bulk part and the boundary part. So there is a competition between the bulk term and the boundary term, and this derives the mean field exponents inside the critical. Okay, so the quadratic variation, so we can prove that. So this variance of this Mk, which is nothing but the Dirichlet pairing, it will be epsilon Fk times E tilde Fk times Fk. And you can, by conditional variance formula, you can derive this Mk prime is variance of expectation Mk prime given Fk plus expectation variance Mk prime given Fk. And this term is again variance of Mk. So variance of Mk prime minus Nk is actually the difference between this zero average capacity. And this E tilde Fk is by definition it is zero average capacity. And then you can prove that the quadratic variation is given by the difference in this zero average capacities. K naught is the initial set of the exploration. And this relation is the key ingredient that transfer the cluster volume to the Brownian motion. Okay, so this is the Dubin-Schwarz theorem. So if you time change the Brownian, time change the martingale with this quadratic variation, then the time changed martingale is actually has the same law as the Brownian motion, whose whose time parameter is given by the quadratic variation, and which is nothing but the zero average capacity of the cell. So this is the Dubin-Schwarz theorem. So after reparameterizing by the quadratic variation, we get a Brownian motion. So this is the main idea of the proofs. Okay, now we obtain the tail bounds for the cluster volumes. So the upper tail bounds for the largest cluster. So if you take H equal to minus a mod V to the power minus 1/3, then the largest cluster has this type of bound. And if you take H is positive, and then the largest cluster has this type of exponential decay. So from these two bounds, for the first bound, if you take is of the constant order, that is the critical window, then the first bound leads to the upper list leads to the volume of the gives a upper bound for the volume of the largest cluster, and which is mod B to the power 2. And if you take A, which is omega of mod B to the power 1/3, which is subcritical regime, then choosing delta suitably, you get that the largest cluster has size log mod. So these are the upper tail bounds. So I will briefly mention the proofs, the upper tail bounds. So you have a large, the size of the largest cluster is at bigger than equals to T. That implies the explored sets in G tilde has size at least T. And then the corresponding martingale values will be bigger than equals to H times the zero average capacity that we have already saw in the martingale result. And then by linear isoperimetry, this will continue until time Tt in the Brownian's time scale, because this time change martingale has same law as the Brownian motion, and this zero average capacity will be bigger than equals to Tt for the size T. And then applying Dubin-Schwarz theorem, this event becomes that Bt minus Ht is bigger than equals to 0 for T belongs to T naught to Ct. So T naught is nothing but the zero average capacity of K naught. And we can obtain this bound for these probabilities using classical Brownian probability computations. So see, H is this is for H less than 0, right? So this is a Brownian motion with positive drift. So for this we get 1 by square root T. And when H will be positive, so this will be Brownian motion with negative drift. So you will get a exponential decay here with respect to T. And that derives the second result of the upper tail bound. So now, so let's complete the proof. So you take, so define this variable nt bigger than equals to T, which is nothing but set of all x in V such that size of the cluster of x is at least T, right? Then by definition of T, probability largest cluster is bigger than equals to T is nothing but probability NT, cardinality of NT is at least T. This is by definition of NT. And then apply Markov inequality to say that expectation NT by T and then less than equals to X in V probability Cx bigger than equals to is T by, if there is 1 by T, and then you take a maximum mod V by T, maximum of these probabilities, and maximum of this probability is bounded by 1 by root T that we observed from the Brownian calculation times 1 by root T. So mod V by T to the power 3 by 2. Then you choose T equal to delta times 1 by delta times mod B to the power 2/3. And this proves the upper bound. And for lower bound, for the largest cluster, so we have similar tail bound. If you take H equals to A times mod B to the power -1/3, we have this type of bound. And when H is negative, we have this type of bound. And again, for when if A equal to order of 1, then you from the first bound you get the lower bound of the size of the largest cluster inside the critical window. And if you take A is omega of mod B to the power 2/3, this is a supercritical regime. And for this, you got that the existence of giant cluster with high probability. So this proof of this part is more subtle. So we will I will give a just brief. Okay. So how much? Okay. So I will give a just brief sketch of the proof. So this is the second part of the martingale remark I was mentioning, that is it true that if the martingale value is large, then you will get a large cluster. So is this true? Because we have these two parts of the martingale, bulk part and the boundary part. So it can happen that the bulk part is very large, and that corresponds, if the martingale value is large, the bulk part is very large, that contributes a large value. But we are not, then we are not inside a, we are not exploring a cluster. So and so if you try to explore initially, start to explore initially, you will get maximum, the largest, the expected size of the largest cluster will be mod V to the power 1/3. So what we will do, so we have to explore more clusters. Then, so let us give a brief strategy what we will do. So we have to obtain that the largest cluster has size at least, right? So we will give the martingale a activation first. So I will ask that the martingale will take a certain square root T value first, because this is because the Brownian time scale of the martingale. And then I will ask that the martingale will be at least, so let's say this is C1, this is C2 root T, at least above C2 root T for a long time. And this long time will be order of T. And if this happens, then we'll get that the largest cluster is at least T. But so if this is true, then this is true. But then we have this bulk term plus the boundary term. Then I have to control the bulk term. Otherwise, I don't know if I am exploring a cluster really. So we have to, so to get a control of the bulk term, so remember that bulk term is nothing but dx, phi x, and this is nu k. And we can prove that this variance of x belongs to k intersection b. Variance of this k intersection b dx phi x, this is bounded by some c times k intersection b. And then this is a Gaussian variable. So I will ask that supremum, let's say k subset of V, and mod k is equal to t and k is connected. So some point belongs to k. Then m k bulk is bigger than square root t. So this is now this supremum is over all lattice animals. So it is this entropy gives you the e to the power c times t, and then this is a Gaussian variable. I can use the Gaussian tail probability to say that it is okay. So you have this nu k. If you add nu k here, so it will be nu k squared, and nu k squared is bounded by, so nu k is, remember, is less than equals to k intersection v, so it is bounded by mod k intersection v cube by mod v square. Right. So if I plug in this, I will get e to the power minus, it will be t, and then mod k is t, so it will be t cube by mod v square. Right. Then you have to have this t less than this mod v square by t square. So from that you get that t is less than mod v to the power 2. And this is how we are getting the critical exponent, mod v to the power 2/3. So this is for this, and next we have also the supercritical result. So there we can also prove that there exists unique giant component in the supercritical regime. And so for Bernoulli percolation on expander, so you have that supercritical, in the supercritical phase giant cluster is unique, but the second largest component is kind of order of mod v to the power omega for omega less than. So in our setting, we observed that this anomalous behavior goes away, and we got that the second largest cluster has volume log mod. And some open direction. So in the critical Erdős-Rényi case, the scaling limit of the critical cluster is known from the famous paper by Erdős, and also recently this was obtained for high dimensional torus. So can we identify the scaling limit for our model? Okay. Thank you.
Thank you, Dipranjan. So are there any questions? So I have one question. So everything is in the Gaussian setting,
Right.
and you can also perturb the model a bit by forcing the vertices to be close to an integer, so a Sine-Gordon model. And in that case, it's still, you have certain bounds on the variance which comes from Gaussian domination. So do you think using these kind of bounds, you would still be able to say something about about the cluster size.
Cluster size in which model?
So you have really the same model, except that at the vertices you slightly perturb the potential, so you force them to be closer to an integer.
Okay.
So yeah, like you can use, like a lot of the analysis works the same. So for example, you still have this Brownian interpolation. You still have the Gaussian potential. And then your model is not exactly Gaussian, but you can still bound, for example, the point-to-point variance by the Gaussian case. So you can see that certain quantities can only go down by doing this perturbation. Can you still say something about the cluster size in that case?
I think if you can compute this kind of tail bounds, which are obtained from this Brownian tail probability computation. So if you have some kind of error bounds in the variance between two components, like Stein's methods or something like that, using that, I think you can derive similar tail bounds there.
Thank you. Okay, let's thank Dipranjan again. And we're going to make a group picture just before the lunch. So let's go outside together, and then afterwards we can have lunch.